Okay. In the last lecture, we talked about analog systems and digital systems. Analog is a natural thing occurring in most of the real life situations. So, we need to have analog signal processing capability. At the same time, we saw digital systems are more, let us say, reliable, cost effective, and are easy to work with, or design and work with, especially for storage and transmission. For these reasons, I said most of the real life systems try to push as much processing as possible into the digital domain, still have an analog interface at the input and output, because all naturally occurring systems, most of the real life systems are having analog inputs. So, this is the block diagram sort of, if you want to think of this as a digital system. Then we have an analog interface, analog in, then we will have the digital to analog converter, analog to digital converter. ADC stands for analog to digital converter, and then goes into the digital domain. I will explain to you why I put one arrow here and a set of arrows here. I will explain to you in a minute. The output of the digital system I have again has to processed by a reverse process, which is called a digital to analog converter, DSA, because I am including all the pre-processing filters and all that as analog in. I am not talking about transducer conversion to electrical signal, mechanical to electrical transduction, or sound to electrical transducer, all those things I am not including. I am just generally saying everything before you convert the signal to digital, I put it as analog. Details of this you will learn in analog course. And likewise, once I have a digital output, I need to have some filtering and all that. I will not show all that. I will simply say it interfaces to the real analog world. And what is this digital system? That is what we want to study in detail in this course. As I said, what are the components of the digital system? What are the properties of these components? How do you analyze these components, and how to design these components for different applications? We may not be able to do all of it in a single course, especially in an introductory course like this, but we will definitely get into many aspects of this. There are more complex designs and more complex analysis may be taught you in future courses, more advanced courses. So, what is a digital system? Are we familiar with any digital system? And can someone give me an idea what do you mean by a digital system? When somebody says digital system, what comes to your mind? Computer. So, first thing you come to your mind is a digital system is a computer. Good. This is the most obvious thing anybody will think of. What else? Calculator is a sort of a computer, right? I will put it calculator. I am not going to say no for you. Something else? Watch. Digital clock shall I call it? Because watch or a clock depends on the size, right? You call something a watch or a clock depending on how big it is. If I wear it in my hand, I call it a watch. If it's on the wall, I call it a clock. Anything else? Digital voltmeter, and I can say digital ammeter, and then I can digital pressure meter. I can say so. We can say measuring instruments. Instruments. See, these are some of the obvious things, especially computer. The first thing that comes to your mind, but you know, today in today's world, almost everything is digital. The Walkman, if you have one, there's a lot of digital component in it. Even though the music finally that reaches your ear is analog, there's a lot of digital processing to improve the quality and equalizing the right attenuation of right type of notes and accentuation or improvement of the type of frequencies that you want to hear. Like that, many things that you go along walking on the road without your knowledge, you will see many things, but you don't analyze them, but most of them are digital today. For example, automobile today, if you take an automobile, a car, so lots of digital features. The engine ignition control of engine has lots of digital processing in it, because to precise timing for fuel efficiency, and there may be other control circuitry which turns on, turns off things at the right moment. Even a car radio that you have, or a car tape deck as you call it in a car, there is a lot of audio and a lot of digital in it, because again the same processing I told you about Walkman. The CD that you the tape that you insert into the tape deck may be an analog tape, magnetic tape, but then the pickup and the processing, a lot of digital involved, so that you have noise free reception in a car which goes at very high speed and highways with so much ambient noise externally as well as internally generated by engine. In spite of that, you are able to hear, listen, they are very good audio, right? That is because of lots of processing. And again finally it will be turned into analog for you to hear through a speaker, but in between there is lots of digital processing. Toys, control equipment at home, you have a washing machine maybe. The precise timing of the cycles, especially in Chennai, which is water starved city, you should not waste water. So to what level should you fill your washing machine, and when should the water flow, when should the water flow stop, and when should rinsing should start, churning or whatever you call it in a washing machine, precisely controlled. In television, you see, you take for granted all these gimmicks that you see on the TV screen. Earlier you used to have a person in front of a camera like this classroom here, and then it will go only this is an analog signal. Television pickup is a sound, light intensity modulation. That intensity modulation converted to electrical modulation. Electrical modulation is sent to the receiver, where it is demodulated as again a light variation, which is apparent picture tube. But today you can see lots of things. You can have multiple, you can have a corner of the screen having my lecture, and the rest of the screen have the classroom, and part of it they can have a subtitle running underneath. All these gimmicks, different gimmicks, are possible because you are able to, the studio people are able to store the image and manipulate it. You would have seen all this video in television programs, in movies and things like that, all these things. So there is so much more. So I cannot exhaust all the possibilities. Measuring instruments, control, I will say control systems. I will put one simple word, control systems. and simply we will say audio video processing. So, it is alright that we wanted to push as much of this processing into the digital domain as possible for the reasons of cost, reliability and ease of design. But how complex the system is going to be depends on the application, that is what I am trying to say. Yeah, obviously a computer, today's computer, we talk of Pentium, P3 or P4, whatever it is called, all these different versions running at gigahertz clock speeds. The complexity of the circuitry inside is enormous. On the other hand, you have a simple washing machine control, I said, or a mixer that is used in a kitchen, domestic kitchen, where all you have to do is to time it for a particular cycle or whatever it is, control on off switch control. So, depends on the application, the complexity varies, depending on the application the complexity varies. So, but so you can't be overwhelmed. How can I learn in one class how to design a computer? Of course, you are not going to learn to design a computer in this class, but we can get well into that, because the other thing I told you about digital systems the other day in the introductory lecture, it is a repetitive nature. It is possible to reproduce, as I said, improvement in the accuracy can be done easily by adding more blocks in a digital system which are almost identical or similar, whereas in analog an improvement in accuracy or improvement in performance comes with a great effort, at the cost of great effort being put in the design. So, improve the performance of analog system, the design efforts are not proportional to the improvement, it is much more, whereas in analog digital system it depends on the effort, it is proportional to the effort. So, that is one thing. So, it is possible to design complex systems, because if you know how to design simple systems, complex systems will be lot of this work. Of course, there is, I am making it too trivial, because there is a lot of control features and all, how to combine all these various blocks into a complex system. It is not a trivial task, it is a non-trivial task, but still it is not as complicated or as formidable as you think. So, basically a digital system design becomes easier because it consists of building blocks. Any digital system can be broken down to building blocks. Let us take an example of a computer again. What are the things you have in a computer as far as you know? Come on, you all use computers. There is a CPU, or there is a CPU, central processing unit, which is what does all your computation, the so called computation. Even though today you use computers for more non-computing purposes than computing purposes, like internet and email. Is that not what we use most of the 80% of the time, and 80% of people, including me of course. I am not going to pretend that I am doing high performance computing in my computer, it is all the same. Maybe my computer is a little faster than your computer, because faculty is given a better computers than what you see the labs, but it is all the same. But arithmetic central processing unit which processes, let us say, let us not worry too much about whether it is computing or processing, is manipulation of data, is also processing, storing and retrieving at the right time, file management, whatever, I will call it processing. So, be non-controversial about it. So, CPU, and then what else do you have? Memory. Memory is required in a computer to store program and data. I need to have a program to run, so I need to store it somewhere, and I need data for input and output, and it is to be stored. And then what? Input output. How am I going to put the input into the computer? How am I going to get the output of the computer? So, input output units. These are standard building blocks which you have been seeing from your high school physics. In somewhere around down in 6th or 7th grade physics book, you would have seen a block diagram of a computer with a CPU, the memory, I/O. I do not think it has changed, but what is, we will know more about it, more and more functions, more and more complex things. Now, like this I can break down any digital system. I can now further divide the CPU into, if I am interested, arithmetic logic function, and if I am further interested arithmetic function and logic functions, and I am further interested an arithmetic function consists of add, subtract and multiply. So, adder, subtractor, multiplier. I can keep on, I can from a top down approach it is called, from a top view, from overall view of the system, any digital system, down to the details I can define, and all I need to do is to design these simple building blocks. I call them building blocks now. So, basically this can go into ALU, control, logic, and let us say register to store results. I am just giving you a very trivial picture, much more to it than this in a computer, and you will learn this in the next course, computer architecture course. But the point is, again ALU can be made up of, ALU is not a black box, you know it has to do arithmetic, it has to do logic. So, what is a logic function, what is an arithmetic function can define. So, arithmetic function can be an adder, a subtractor, a multiplier. So, I can design each one of them and put them together. So, I can go on dividing the task, dividing the partitioning the system into smaller and smaller subsystems. So, from systems I get subsystems, these are not standard definitions. Subsystems can be broken into modules or functional blocks if you want to call them. And functional blocks can be downgraded into basic units. I will not elaborate at this time because of this first course, we do not have some of the background that you need. As an example, I can say I can have a gate level implementation. A gate is a concept. I have two inputs and an output. So, depending on the gate type, the output is defined in terms of the input. The gate is only a logical building block, but how do you realize it? You need transistors, resistors and capacitors. So, from this basic units to actual circuits using active and passive elements. So, now if you think of a computer like this, it becomes much more manageable task. Like that I can think of memory, like that I can think of I/O. So, any digital system can be broken down into subsystems, subsystems can be broken down into modules, module can be broken down into functional blocks, functional blocks can be broken down into logic units, logic units can be broken down into circuits. Circuits are made up of devices and components. Circuits are made up of but you do not need this, you did not read it when you were high school physics, or many of the users of computer today who are, they do not know what is inside a computer. For them it is a computer, only turn on and then type in the keyboard and they should get the message they want. If they do not, so they say this computer is not working, it is broke, they make they call the person and then yell at that fellow, what is the computer have given me, it does not work, and all that type of thing. That is all they do. So, we are a little more than that, we are supposed to be designing these things, electronics, electrical engineers, we are domain specific people, we have to design these things. So, that is why we are having this course of digital system. What does the basic digital system consists of, what are the units? So, in this first course obviously you cannot start from here and go down, you have to start from here and go as far as possible, but at the same time we will always have this goal in mind, so that at any point we will be able to expand into different schemes. Of course, again I will not go into devices and components for two reasons. One is that this course electric magnetic circuits, you have a course, and then analog circuits, these are the things which will be covered in more detail. So, we will probably start with basic units and functional blocks and modules, and if possible subsystems, and maybe give one or two examples of a system design also at the end, but need not be a computer. Computer is only a concept. Any digital system has the same type of hierarchy, as you want to call it, hierarchy, from top to bottom, from system to circuits to devices to components, the same hierarchy is there whatever is the system. Now, everything is a computer in one sense. If you think of computer for a moment not as a machine which computes, as I said, many of us do not use a computer for computing today. We do not need computing in my work. Many people do not need computers in their work. There are people in the offices, in the banks, of course banks may add and subtract, I do not know, but there are many applications where computing is not required to be done by a computer. It controls data, it keeps data, it acts as a memory database, it gives out information when it is needed. So, when you think of a computer for a moment, forget the fact that it computes. Any function that you want to implement will need a central processing unit. That process may not be computing, it may be control function, it may be just storing and releasing data at the appropriate time. Whatever it is a control function, it is a central processing unit, so processes the data that you give. Processing is just keeping it and releasing it at the right time, is also processing to a certain extent. And then any system needs a memory to store the program. What do you want to, let us say we are analyzing the railway reservation. Railway reservation, all of us know it uses computers. We go and stand in front of a line, in each window there is a computer, the fellow keeps punching in numbers in a keyboard. So, for anybody including us, the so called electrical engineers, it is a computer he is working on, more so for a person who is not related to electrical engineering or even engineering. But does he really do any computation there? He finds out the availability of seat in a particular train that you want and allocates a seat for you in that train and says that seat is taken, so that that information is stored, so that next person comes, the same seat is not allotted to that person. Will you call it a computer? Yes, it is a computer. Does it process? Yes, it processes. What does it process? It processes data that the fellow gives in and gives it the proper response as an output, all in terms of information in this case, right. Information processing is also computing. So, if you now think of a computer as that, most of the things you can relate to now as a computer. A traffic light controller, can it be called a computer? Yes, it has to know which street has vehicles waiting, how long has this street been having a red light, is it time for the red to change to green in that road and release the traffic. So, the other street where the data traffic has been flowing for the last few minutes should now be stopped and the green has to change into red there. It is all processing, is it not? It is all processing of information. So, anything can be related as a computer. If you think of that as a digital system, as a central processing unit in which your desired task is performed, be it a computation task or a control function or a data information processing or a data storage and retrieval, whatever is the thing that you want that system to do, it is doing it. So, that I will call a central processing unit, and I need to know the program to do this. For example, traffic light controller cannot behave arbitrarily, you have to program it. Look at this street A, B, C, D, 4 streets. Look at street A, see how many cars are waiting, how long it has been red. Based on that, go and put street B as red, release street A as green. This is a program. So, it needs a memory to store this program. So, program memory is required in any digital system, whether it is a computer or not, and the data has to be there in some form or other. Sometimes trivial, sometimes more. In a railway reservation, data storage is a huge thing. How many trains, what are the timings, and how did the fare, how many seats have been given in GT Express, and some of the other train systems like traffic control, there may not be much data to process. All it needs to process probably is the timing, how long it has been on, how long it has been off. So, data memory is required, program memory is required, central processing is required, input and output are the thing. In the case of the railway reservation system, input is the key operator, output is the printing that he gets. In the case of traffic light controller, the input is the some sensor that you have somewhere to say how long it has been on, or some sensor, somewhere you have to see how many cars are waiting, and the output is the lights turning from red to green to yellow. So, now if I think of this as a model of a digital system, I can call everything a computer. A toy is a computer, a washing machine is a computer, your remote control and a TV is a computer. You did not think of computer like this so far. I do not think, I do not know, at least some of you might have, but most of you do not, right. Most of you did not know that we are working with 10 to 15 computers a day. You all crib that we do not have enough computers in the department, but each of you have 15 computers. Your cell phone is a computer, it has a program, it has a data memory to store your numbers, it has a program memory, it has a memory to charge so that your parents can pay for it. It is a computer, is it not? A cell phone is a computer. I would say a cell phone is a computer. How many of you disagree with me? Are you at least convinced that it is a computer now? So, when you are thinking of digital system design, we are going to see how to make this, build these systems to control it in a way that we want a desired performance out of it. A chemical plant monitoring, temperature monitoring in an oven, air conditioner, right temperature to be set in, elevator, lift, control, going up and down, which floor has a call button pressed, which floor destination has been pressed, analyze, process and do the motor which takes the car up and down, elevator car, the lift car up and down to operate it properly. When you press floor 4, you do not want it, the motor to land in and the car to land in floor 5, you want the car to land exactly in floor 4. How does it do that? It is a computing. So, anywhere I can think of now the system design, that means all you are interested is, that is why some of these books, digital design and digital logic and computer design, the same book is called, but computer is, do not take computer too literally, because nobody uses computer to compute nowadays. Very few people who are aerodynamics and all those people who write equations, 100 equations with 100 parameters each, those are the people who are really using the computer for computing, but most of us do not use it for control function, information storage, retrieval functions. If you think of computing as that, then all you have to do is to, what are the basic building blocks, how do you build these basic building blocks into system which is useful to us, which are useful to us, like a traffic light controller, like an elevator controller. That way I will be able to probably do this also in our course. We will probably start with the basic units. As I said, circuits and device level I will not do it, because there are other people who are going to do it more competently. From basic building blocks, how do you define functions, how do you make these functions into modules, and how do you make these modules into subsystems and possibly into system, because our traffic control is one of the simplest subsystems I can think of. So, I can design it in the class at the end of the course, probably. Let us see how far we go. It is too early to say, it all depends on how effectively I am able to transfer information to you, how effectively I am able to absorb the information. Let us set that as a goal, at least some of those things we will do. So, that is the crux of this course. That means we start with this basic units, and what are the basic units of building blocks of this. Now, before doing that, we have to do a little bit of change of gears. We talked about digital system being, the last class if you remember, in the first class, introductory class. If you remember, we talked of digital system as a system in which discrete levels are defined for the quantity you are considering, either voltage or current. For a moment we will stick with voltage, most of the course will stick with the levels being voltage levels, it is also being current logic, voltage. So, let us talk of voltage as 0 to 5 volts, I gave you the example of 0 to 5 volts that day. Now, we said we wanted to define in an analog system, a system or any variable of the system can take any value from 0 to 5 continuously. In a digital system, I said there are only certain discrete levels between 0 and 5 which are allowed to be taken by the parameters. Is that not what we said between the difference between analog, discrete and digital the other day? Analog system, time varies continuously, the variable varies continuously, within the parameters, within the limits, any value is allowed. In a discrete, parameter can take any value, but we will only look at it at discrete intervals of time, discrete data systems, discrete time systems. In digital systems, we will look at this only at discrete times, and also we will only recognize certain values of the parameters as allowed values, and any value in between will be rounded off to one of those values allowed. Was that not the definition I gave you? Any doubts on that? No. Now, on one hand we say we can have an accuracy improvement, easy to improve resolution, but I say only certain values are allowed. That means the question of how do you make a system more accurate if you want to. For example, you have a class, I have this class, okay, let us say with all these exams, quizzes and final exam, total marks for 100 is for 100, 100 I will grade you. So, can I have those who get less than 50 fail, those who get above 50 pass, no grades, or I will say those getting above 50 get S grade, those who get less than 50 U grade. If I say, will you agree? If you say 10 above S and less than 10 U, you will agree. But if I make, or if I put it this way, supposing I said those who get above 80 S, those who get below 80 U, will you agree? Okay. So, this is digital system, only two values are allowed between 0 and 100, one is 0, the other is 80. First, the part of the class will be mapped between 0 to 80 and will be called 0 marks people. People who got 80 and 100 will be mapped as 80 marks people. 80 marks people get S, 0 marks people get 0 U. But I want to improve the resolution, you do not want this, this is unfair you will say, right? Then nobody will register for my course next semester. So, I will have to at least have different grades, 20, 40, if possible 15 anyway. 20, 40, 60, 80, reasonable, more reasonable fellow he is, even though I would like to have S, he got at least A for me. Okay. So, I want to improve the resolution, that means I have to have more levels. But I said only two levels are allowed for variables, variables are only discrete levels are available. So, voltage is 0 to 5 volts. How do you represent what it is? Because as I said, the storage and transmission is more reliable than digital, because we know that it has to be one of the values which is allowed only has been transmitted. If the value received at the output is not the same as what has been transmitted, we know what could have been the value, assuming a reasonable error. I gave you the example, if I am trying to pass 1.25 volts and I got it as 1.28 volts, you can in all probability say this fellow tried to put 1.25 volts, some noise got added and became 1.28, so I will correct it to 1.25, you will say. Similarly, you will try to set 1.25 volts and you received it as 1.22 volts, you know this fellow tried to send 1.25, by it got some dropped, some voltage got dropped in the line. So, I got 0.03 volts less, it is only 1.22, but I am sure that this fellow has spent 1.25 volts. So, I want to improve the resolution, at the same time have only fixed level, that means I should have more than number of digits. So, if in a digital system where we are used to number systems, we have these digits 0 to 9 depending on the accuracy. Supposing I want to have 10 levels, I can use 0 to 9 levels. Suppose I can have 20 levels with 2 digits, I can have 20, but it is an inefficient use. With 2 digits I am going to use, I can even have 100 levels, 0 to 99, right. So, as I increase the number of digits allowed to be used by me, I can represent the quantities more and more accurately, more and more precisely. Now, you translate to digital system, I want to have this physical device, this basic unit circuits and functional blocks to recognize discrete levels. If it is only 2 levels, no problem, 0 or 5, as I said U or S. Then I need 2 voltages, 0 volts is 0, 5 volts is pass, 0 volts is fail, 5 volts is pass, in between nothing. We do not want that. So, I want more levels. That means, how do you have more levels in an electrical circuit? Because after all, the whole thing is finally electrical circuits. We have to give voltages as inputs and measure voltages as outputs, can also be current, but as I said I am going to stick to voltages in this course. Whatever is the electrical parameter or even non-electrical parameter, pressure can be, temperature can be, anything, I need to have a way of representing more than 2 levels or any number of levels in my system, but that means my circuit should be able to represent 0 volts or 5 volts, fine. If I have 0 volts, I will show it as a 0, 5 volts I will show it as a 1. That means I have a switch. If the switch is open, I will say no voltage is passing through. So it is a 0. The switch is closed, the entire 5 volts is passing through. So it is 5. So I can have 2 levels. If you want 4 levels, I need to have 2 switches operating in together. If both the switches are on, I may have one possibility. If one is on, the other is off, I may have one possibility. I have 4 combinations now. So this is what is known as number representation. Before we go to the basic units and define them, I would like to tell you a little bit of number representation. All of you know this, I just want to make it a very simple presentation. Most of it you can read it by yourself in any standard book, and all of you might be knowing all this by now in your so called computer sciences course in your high school. What I mean is, we have only 2 levels. Let us first make some assumptions. Assumption in this course, unless otherwise stated, we work with voltages. Unless otherwise stated. Two, the voltage levels are 0 and 5. Range are 0 volts and 5 volts. Range is 0 to 5 volts. Now we have only 2 levels representation, like pass or fail. I can have pass as 5 volts, fail as 0 volts, no problem. How do I do it? By means of electrical switches. A switch can be open to indicate a condition, closed to indicate another condition, on or off of a switch. Or if you want to have a non-electrical representation, I can have a flag here, and the flag is up, it is 5 volts, flag is down, flag is up, your pass. Each person comes to me, I will give the grade, today is a great day, you come to me, I will raise my flag if you pass, I make the flag go fail. Simple, but you are not happy, you want to know whether pass with S grade or A grade or B grade, so I need more flags. Pass with A, I will have one extra flag, pass with B, I have another flag. So as I go on more and more, but then these flags are same or switches are same, I can't make a switch half closed. Can I make a switch half closed, half open? No. So I should have more switches can do the job, is it not? So with these 2 assumptions I am going to do, if I only have to represent 2 numbers, 0 as 0 volts, 1 I will call this is a symbol, it is not a number in this case, it is a symbol. So 1 is 5 volts, 1 is on, is equal to off, of absence of a flag, off, the switch being off, flag being absent, or anything else you can imagine. See, I want 2 symbols, I say. You can have a red shirt and a green shirt. If I wear green shirt today, you are pass. Red shirt. After all, you want representation. How does it matter? One is on of the switch, presence of a signal. But as long as there are 2 numbers, there is no problem. But the problem comes, I want to have more than 2. I want to improve the levels. I want to have 10 levels. I want to have 100 levels. Now in the case of binary, this is binary numbers, there are only 2 positions possible, 0 and 1. Fortunately for us, we do not have to go from 10 to 100 to 1000. there is in decimal systems, decimal numbers, each digit is 9. So, only one digit I have, I can represent 0 to 9. If I have 2 digits, I can represent 0 to 99. If I have 3 digits, I can represent 0 to 999, 999. So, it increases by a decade, by 1 decade they call it. In a binary, fortunately only 2 levels. If I have 1 switch, I can use 2 levels. If I have 2 switches, by a combination of these 2 switches, I can indicate 4 levels, 2 power 2. If 3 switches, I can indicate a combination of 8 levels. So, depending on the number of levels, I can represent these by different switches. So, for example, if I want to have 4 levels, I can have 0 0 0 1 1 0 1 1. As I said, these are symbols, do not think of them as numbers 0 and 1, 0 symbol and 1 symbol. That means I can have switches which are off. I will have 2 switches, if both are off, I will see 0. If it is off and on and off, switch 1, switch 0. Switch 0 is off, switch 1 is off, number is 0 0. Both switches, one is on, the other is off, it is 0 1, and then both are on, it will be the 4th level. So, 0 to, so 2 switches can give you 4 levels. So, in terms of this, that means any number can be represented now. I can now increase the range or the accuracy or the precision or whatever you want to call it. I do not want only 2 levels, I want 4 levels. The discrete parameter, the digital parameter, the voltage or a current, I said mostly voltage, but whatever parameter I am monitoring, which can only take discrete values, can now be allowed to vary over a wide range. If I did not have this, if I had only one switch, it can only take a value of 0 or 1 or 0 or 5 volts, 0 volts or 5 volts, or symbolically speaking 0 or 1. If I have 2 switches, now the same discrete, the same parameter is allowed to take 4 discrete values, namely 0 0 0 1 1 0 1 1. If you translate it into voltages, it will be 0 volts, 1.25 volts, 2.5 volts, 3.75 volts. Do you understand what I am saying? So, the 0 to 1 volt can be mapped, 0 to 5 volts can be mapped as 0 volts and 5 volts with 1 bit, with one switch, with 2 switches, it can take 0, 1.25, 2.5, 3.75. With 3 switches, it can take whatever, divide by 8, 5 divided by 8 is 0.675, right? Is it right? Yes or no? We're going to say yes, 0, 0.675, etc., etc. That means now I can, what I told you in the beginning about, you can increase the number of the representation to be more accurate by simply having more switches. A switch design is same. Supposing a switch has been designed by a circuitry using a transistor, need not be an on off switch. Now all I need to do is 2 times I have to do it, 3 times I need to do it, 10 times I need to do it. If I have 10 times, I have 10 switches, I have 2 power 10 levels. 4 switches, I have 2 power 4 levels. 3 switches, I have 2 power 3 levels. 7 switches, I have 2 power 7 levels. But they are identical switches. So my job of improving the accuracy or representation of the number becomes easy. This is called binary representation of numbers. So now you know all of this about binary representation. I am going to make it as a reading assignment. I don't want to spend a lot of time on this binary number systems. Is there anyone in this class who does not know what a binary number is? Do all of you know binary systems? Does anybody tell me? Because even there I am going to teach it, I can tell you at least where to read this. So now I have a decimal number and a corresponding binary equivalent, binary representation. Now 0 will be 0, 1 will be 1, 2 will be 1 0, 3 will be 1 1. So, with the two binary digits, binary digit is called a bit. 1 bit will do, 2 bits, 4. A bit stands for a binary digit. Like that I can go on writing any number. So, depending on how many levels I want the discrete value, the parameter, how many discrete values I want my parameter to take in the given range of 0 to 5 volts, I can define the number of bits I will use to represent that number, that is all. So, I can decide on the number of bits which will be used to represent that quantity, but still it is discrete. Even if it is 10 bits, 0 to 1023, 10 power 2, 10 bits is 2 power 10 minus 1. So, it is 0 to 1023. 0 to 5 volts can be divided into 1024 steps starting from 0 volts, but all of them are discrete. In between those discrete steps the parameter cannot take the value, but it is good enough for me. I am not going to have more accuracy than that depending on the system. If it is, as I said, is a train coming or not, flag will do. If it is a mark in a class, there are grades in a class, there may be 5 levels, may do 8 levels, may do. If I want to represent the number of people in this class, a finite number of bits will do. So, if I want to count my money, some finite number of bits will do. Depending on the application, the population of this country, how many bits are required. So, for every application there is a finite number of bits required, and that will decide my precision or the accuracy of my digital system, and all of them are reproduced identically. So, my improvement in the accuracy or the precision of the digital system, the improvement is not at all difficult, because all I do is to replicate, as I call it, duplicate, actually replicate, do it one more time, that is called replication. So, I will leave it as an exercise to you, reading assignment to you, to do the following things. Reading assignment, conversion of decimal to binary, decimal numbers to binary representation, that is the right way of saying it. Conversion of binary representation to decimal numbers. Do it for integers and fractions. I am not going to treat this topic further. I will assume that all of you know it, because I know these topics are being taught these days in schools. No point in going on repeating things which you already know. But if any of you have any questions, you can ask me, and as I said, we will have a discussion class in which you also can ask me. So, you practice these things yourself. Take any number, I don't need to give you homework on this. You take any arbitrary number, start converting to binary, and take any arbitrary binary string and try to convert it into decimal, and do it. What will happen is a fraction also, that is integer and fraction and combined mixed number also, real number, that is both integer and fraction together in one representation. So, that will now give me, that means I will only deal with 2 levels of any variable, but by repeating these variables in different positions, bit positions, I can get better resolution of my system. That is what I am saying. That way we do not have to worry about my digital, I have only 2 levels, 4 levels, how can I accurately do the processing that I want in using computers. Okay, we will stop here. In the next class we will start looking at the logic blocks, basic building blocks of the digital system. you.